In this video, I want to demonstrate the paired sample t-test, otherwise known as the repeated measures t-test. It's used when one group of subjects is measured on an interval variable at 2 points in time, such as when you are conducting a program assessment and gather data before and after the program on the same group of people. A control group is not needed in this case, as participants serve as their own control group. Now, if one was doing a pre and post test on the same group of people but the outcome was dichotomous, the two-sample or group test of proportion is more appropriate. To demonstrate the paired sample, aka repeated measures t-test, let's look at some hypothetical data. Here we have both pre and post-program test scores, representing % correct, for a sample of 20 individuals. As you can see, for the majority of individuals, their performance improved, though the magnitude of that improvement varies. In other cases, there was no improvement or even a small decline in performance, as may be the case. The question is, did the program have a significant effect on test performance? In other words, can we be confident in rejecting the null hypothesis that there is no difference in means between pre and post test scores? To run the paired sample t-test, one can input the command directly. Simply type t-test. In this case, our variables are pre and post, so pre equals post, and hit return. To go through the menu system, simply click on Statistics, Summary Tables and Tests, Classical Test of Hypotheses, Mean Comparison Test, Paired Data. Here, we'd simply enter our two variables, pre and post, and click OK. In the results, we see the number of observations for both the pre and post test group, 20, they are the same individuals, the pre and post test means, and the difference in means. Now, notice how they calculate the difference, simply subtracting the post mean from the pre mean, hence the negative value in this particular case. So ordering matters. A t-statistic is calculated by dividing the difference by its standard error, resulting in a value of negative 3.1383 with the degrees of freedom of 19. Using a two-tailed test of significance, we see a p-value of 0.0054. Now, if our alternative hypothesis specified a directional effect, namely that the program would improve scores, we would expect the difference to be negative, again due to the fact that we're subtracting the mean of post-program test scores from the mean of pre-program test scores. Again, much depends on the ordering of those categories. We would look to the left side in this case, where our alternative hypothesis is that the difference is less than 0. Here we see that the p-value is 0.0027, exactly half that of the p-value for the two-tailed test. Either way, we see a statistically significant difference in scores. While we can be confident in rejecting our null hypothesis and embracing our alternative hypothesis, what can we say about the size of the effect of our program on test scores? Here we could calculate Cohens D. Cohens D indicates the standardized difference between two means and expresses this difference in standard deviation units. The formula for Cohens D is the difference in means divided by the standard deviation of the difference. Unfortunately, the user-written command for Cohens D in Stata does not function for paired sample t-test, but we can calculate it on our own using Stata's computing function. In the command window, simply type display, and then we can be a little fancy and in quotes say Cohens D equals, quotes, and then here we simply will input the difference in means divided by the standard deviation of that difference. So it's going to be 3.7, again absolute value is fine, divided by 5.272571. Go ahead and hit return. And we see we have a Cohens D of 0.7017. Using the following rough guidelines, we can say that the program has a large effect. So that's how you conduct a paired sample t-test in Stata. Hope it's useful.